Hello everyone, my name is Eduardo Tusa and together with Cristian Ramón, Andrea Hidalgo, Jofre Cuenca, Carlos Loor, Marco Takuri, José Luis Ordóñez, Leiden Carrion and Miriam Zumba, we are going to explain the kinematic analysis for modeling the layout of a 2D road curve in Mathematica. We are from the Technical University of Machala in Ecuador. And the content of this presentation is going to start with a problem statement. Then we are going to explain about our approach. Then we are going to describe our results. And finally, we are going to mention brief conclusions regarding this project. So what is an horizontal curve? So a horizontal curve provides transition between two tangent lengths or road weights. As you see in the figure, we can identify the point 1, point 2, and point 3. Point 1 is the point of the curvature at the beginning of the curve. Point 2 is the point of tangency at the end of the curve. And point 3 is the point of intersection of tangents. So why the horizontal curves are needed? So it generates gradual change in direction with a direct point of intersection. Is not feasible in highways, interstate, high-speed roads with constant flow of traffic. So what considerations for design we need to take in mind? For most part, design speed is used as the overall design control. There exists, however, an appropriate relationship between design speed and curvature. So what is the problem that we want to focus in this project? How to elaborate a program to analyze the kinematics of a vehicle in a road curve. So the objective of this project is to present a program that takes as input variables the geometric data of 2 points, let's say point 1 and point 2, on the ground to analyze the kinematics of a vehicle in a road curve. Okay, so it's time to talk about our approach, which is basically in 5 steps. We start by determining a control point, then we determine a Bézier curve. Third, we compute the length of the curve in order to go to step 4 for reparametrization of the curve, and finally we compute the degree elevation of the curve. So to determine the control point, given 2 points P1 and P2 and the respective angles θ1 and θ2, we use the linear equation slope and a point to compute 2 linear equations by using the slope given in the equation below. And since we have 2 linear equations, we compute the intersection in order to obtain the third control point. So we have point 1, point 2, and point 3. So with these 3 points, we are going to use the Bézier curve formula based on Bernstein Polynomials. So the Bézier curve of degree n is given by n plus 1 points. So if a Bézier curve of degree 2, as given as the last equation, it needs at least 3 control points. So since we have this linear combination of Bernstein polynomials, we can express the certain formula as separately as point coordinates, because we are going to have x trajectory and y trajectory, and the Bézier curve basically is a parametric equation with the parameter is t. In this case, our parameter t changes from 0 to 1, and this variation determines the shape of the curve between point 1 and point 2 by using this pointer 3 as part of the control points. Since we have already the curve, we compute the length of the curve by using the first derivative of the x and y trajectories and the formula given in this slide in order to do the reparametrization of the Bézier curve. Remember that we need to that the t parameter of the Bézier curves goes from 0 to 1, so we need to incorporate the velocity design, or the design velocity, in order, or the design speed actually, in order to define what is the time that it will take for a vehicle to go from point 1 to point 2. So this reparameterization is given by the equation in this slide, the length of the curve divided by the design speed. The design speed is given by the Ecuadorian road standard NEVI 12. And once you get the reparameterization of the curve, we did an improvement. We elevate the degree of the curve. How do we do that? We incorporate another point. Well, actually we incorporate 2 new points and remove the point of intersection already computed. So we're gonna have a Bézier curve of degree 3. We're gonna have a Bézier curve of degree 3, but we are gonna use 4 control points. So the 2 additional control points P4 and P5 are given by these equations by using the intersection point computed previously. So let's start describing the results. So what you see now is the Bézier curve of degree 3 with 4 control points given in this analytical expression. You will see the point 1 and point 2, they need the angles of these points. And then we have point 4 and point 5. These are coordinates, real coordinates of a curve close to our university. Since we have the trajectories in x and y coordinates of the curve, we can compute the first derivative and compute the magnitude of this first derivative and obtain the velocity magnitude over speed. And we compute the speed at 5 different design speeds: 100, 90, 80, 70, and 60 kilometers per hour. So that's what you see. So what you see is the vehicle at the beginning is decreasing the velocity as it's going through the road curve. Then it gets or reaches a minimum velocity or minimum speed magnitude, velocity magnitude, and then start accelerating. This process of decreasing and increasing the velocity you can appreciate very clearly in the acceleration, in the tangential acceleration, which is given by the second derivative of the x and y curves. So you can appreciate clearly when is negative acceleration, when is the velocity decrease, and the positive acceleration when the velocity increase, given by the 5 different design speeds. And finally, as I mentioned before, the design speed it's important as the curvature. So we compute the curvature since we have the parametric equations of the Bézier curve and x and y coordinate. We can compute the radius of curvature given by this equation. So the radius of curvature tells you what is the radius in each point along the curve. So most of them reaches different minimum values at different design speed. So as a conclusion, we can mention that the geometry can be modified through the control points of the Bézier curve. The speed is variable along the trajectory. You will see that we have tested by 5 different design speeds. If the geometry is modified, the speed and acceleration also change. The point of greater curvature decelerates, but immediately begins to accelerate at constant variation of the speed. I have to say that this project was developed by junior students of civil engineering at the Technical University of Machala, and it was recognized by the National Network for Research and Education of Ecuador, CIDIA, in the Wolfram Technology Conference 2016. Thank you very much for your attention.